this video, we'll talk about Microsoft's NTFS file system, the New Technology File System. The New Technology File System came out in about 1993, and it superseded the FAT file system. And it made tremendous improvements in terms of performance, reliability, and for security, the inclusion of access control lists. The file system is particularly the master file table, which replaced the root directory under the FAT. Is much more complicated, so we'll take a good look at the details of that.
NTFS is the primary file system for Windows NT, and believe it or not, although most of you might not even have heard of that, that's still in use by a lot of organizations. Or if you're running Windows 2000 or XP, if you're running Windows 98, you might be running FAT32. And if you're running Windows 95, you're most likely running a FAT16 file system. The NTFS originated from the Microsoft and IBM OS/2 operating system, and the file system was called the High Performance File System. So it was somewhat similar to other modern file systems, including NTFS and all of the Linux and Unix-based operating systems, and the Mac OS X High Performance File System and File System Plus. NT was the first Microsoft operating system that used NTFS, and there's actually been quite a few versions of NTFS, as we will see, and all those are backwards compatible. But the reason this was created was it was allowed backward compatibility with the high performance file system. However, this is no longer the case, and there were business reasons for that, not technical reasons, that Microsoft no longer provides backward compatibility with HPFS. Similar to Unix operating systems, and this is Unix file systems, everything is a file. If you recall from our discussions of the FAT file system, you had reserved areas in the file system that were not files. You had a boot sector, you had two FAT tables, and you had a root directory system. Those were not files. However, under NTFS and Linux and Unix file systems, everything is a file. Under NTFS, the first section is the partition boot sector, and it can expand from up to 16 sectors. And then immediately after that is the master file table. And the master file table is roughly analogous to the root directory under the FAT file system. And the MFT, as it's typically called, will be the first file that you will see on the disk. And as I said before, it's akin to the root directory under FAT. And it's created at the same exact time that the volume is NTFS formatted, and it typically consumes about 12.5% of a disk. However, if you have lots of small files, it can be as much as 40% of your disk. So what kind of advantages does NTFS have over FAT? Well, one of the advantages over FAT is that it saves a lot of space. If you recall that the clusters are going to be smaller for smaller drives, let's think for a second, what is a cluster? A cluster is a collection, a contiguous collection of sectors, and the sectors is going to be how many bytes? 512 bytes normally. And so clusters can range anywhere up to a single sector per cluster, all the way up to 64 typically. And so what this table is showing is for the drive of sizes from 0 to 512 megabytes, there is one sector per cluster, and of course that'll be 512 bytes. Notice that as the drive size gets larger, the number of sectors allocated per cluster, remember a cluster is an allocation unit, so a cluster or allocation unit is the smallest size space that can be allocated for a particular file, no matter how small it is, that it ranges all the way up to 128. And so here you see under NTFS the sizes of the clusters. Another distinct difference is the fact that NTFS can now has a capability of representing information in Unicode. And Unicode is just a way of representing characters. So as we recall under when we were talking about ASCII, that ASCII is represented by 8 bits. That is a single byte, which means that there are only 256 possible characters, 2 to the 8th, characters that can be represented by a byte of information. However, some time ago it was realized that there's a lot of languages that can't be represented, outside of course English and some other languages, by the ASCII character set, and so Unicode was created. And so now if you look at the Unicode character set, that is represented by 2 bytes, and so 2 to the 16th is 65,536, which means that there's the possibility of representing 65,536 possible characters, which means that now you can have an internationalized set of characters for any operating system. For Western alphabets, the first bits are the same as for ASCII. So what we'll see later on is that you'll see the first 8 bits are actually represented and the last 8 are null. And here you see the character set right here. If you look down here, you'll see a 1.2.3.4. Since this can be represented as ASCII, there's no need to utilize that extra 8 bits. And so those extra 8 bits are null. And so this is an ASCII representation of numbering system right here. And down here, this is actually from a root directory entry. If we take a look over here, this is actually the name of a file, abcdefgh.txt. And if we look down here, we see a.b.c.e. and so on .text. And this is the Unicode representation of it. And of course, if you recall what this is, if we take a look up here, these are actually different files, this file and this file down here. This file and this file are related. Do you know how? This is going to be the short version of the name, the short name. Notice the tilde here, abcdef tilde 1.txt. So this is going to be the short name of this file. And then the long file name is abcdefghijklm.nop.qrstuvwxyz123456789.txt. So the actual file name is this long file name, and this is the short file name. And this is a completely different file up here. But that shows you the difference between ASCII and Unicode. Okay, looking at the NTFS disk structure and comparing it to FAT, recall that under NTFS, everything is stored as a file. And so if we compare these two, the FAT and NTFS, here we have this small reserved area, which is the master boot record, and you do have one of those for each file system. And then under the system area, you have the 2 FATs right here, and then the root directory area. And this is all system area, and that's reserved for the system. And then you have the data area. Notice under here, as you have everything is pure data area, including all the housekeeping files that are used to keep track of everything that's going on with a file system. And there's quite a few files that are actually a part of that. And these are some of in fact, this should be all of the files that are used to keep track of the files under the NTFS file system. So we have the master file table, we have the mirror of that, a log file, a volume, and we'll go over each of those in depth shortly. Attribute definitions, the boot map, the boot, the bad clusters, the secure area, the uppercase, and so on. Notice that each of these starts with a $sign. That's just typically used by to represent the fact that these are system files. In other words, they're not directly accessible by the user, but the operating system uses them to keep track of the files on the file system. So the master file table, again, is roughly analogous to the root directory. It includes much more information. It includes information on system files, and it's not like the FAT at all, really. we see that under the master file table, the first 15 records are reserved for the system file. So the master file table will actually have records for each of these systems files in here. Okay. Interestingly, the master file table also has an entry for itself, as we'll see shortly. And the records are referred to as metadata, and we'll see that each record holds a lot of metadata. Okay, so here we see that the metadata for each of these files within the master file table, we have the file name, as we see it earlier, the MFT, the system file name, the record position, it's the first one. Remember, we're doing this like C. Stop that. And it's the base file for each file. Here we have the mirror. And the mirror, if you recall, under the FAT file system, that there were two FATs. And do you recall why we had two FATs? The reason was that if one was damaged, then the second one can be used, so it provides a little bit of redundancy. We have the same kind of thing here, and so that if any of the first 4 records of the master file table are, and that's backwards, a little dyslexic there. The master file table mirror holds the first 4 records of the master file table, and it's essentially a safety backup if the single sector fails. So you'd still be able to boot. If you had severe damage to your master file table, you wouldn't be able to boot or read anything off the hard drive. The log file we'll be looking at later is a file that records transactions, and it's stored to allow recovery in case of a system failure. And what we'll find is there's lots of information that forensically that we can recover from a log file, even the entire contents of files. So even though you may delete a file, let's say a small file, from the file system, and you wipe its contents, that is, you perform a secure delete operation, you still, if the file is small enough, may find all the information on that file in the log file. And we've actually done some research to show that that's the case. Then you have the volume system file, which is information that's specific to the volume, such as the label and the version number. We had the attribute definitions in the 5th record position, which lists attribute names, numbers, and definition. Then you have the root file name index, which is at position 6. I know this says 5, but if we're starting with 0, that would be 6, which is the root folder on the volume. And we have the bitmap, which shows which clusters are in use. Now, where did we have that before on the FAT file system? That was located in the FAT, in the first FAT and the second FAT. That's indicated, that's held here in what is called the bitmap system file. Then we have the boot, which is the boot sector, which is used to mount the volume during the bootstrap process. We had the bad clusters, which lists the clusters with unrecoverable errors. Where did that occur before? Under the FAT file system, you recall, that occurred in the FAT area, in the FAT1 and FAT2. If there was a bad cluster that was listed with an F7. And you have the secure, which is a security file, which has unique security descriptors. This ACL stands for Access Control Lists, which is something you should have already had with my course in Computer and Network Security. So what this does is the Access Control List indicates what users have what privileges for a particular file. Then you have uppercase, which is an uppercase table of numbers, which converts lowercase characters to uppercase Unicode characters. And then we have the extends file, which is an optional extensions that are listed here, and then the rest of this metadata area is reserved for latter use. Okay, unlike the FAT file system, NTFS, under NTFS, all files and folders have attributes, and the attributes include the name of the file and the folder, and security information and data associated with it. So there's quite a bit of metadata information that's associated with both files as well as folders. And as we'll see, each attribute associated with a file or folder has a unique attribute type code that we will see shortly. Okay, every file and directory has at least one record in the master file table, including the master file table itself. Files and directories can have more than one master file table entry, and each record, that is, each master file table record, is identified by a unique 64-bit file reference number. And so there's actually a 16-bit sequence number that goes with that, as well as a 48-bit file number. And if we go here, what I've done is that I've opened up a file. Let's open up one more. I've actually done some pre-work here for you to show you where a lot of this information resides. But let's go back here and open up another file. So if we look here, this is the first. I've actually opened up the master file table in Exploits Forensics. You'll see the header for each master file table record is file 0. So actually right here you have one record and then a second record right here. If you look right here, you see the $MFT. So we're actually looking at the master file table record within the master file table. Here we see the master file table, mirror is the second record entry. We can scroll down and see the log file second, and so on. So the master file table mirror is a copy of the first 4 records of the master file table for recovery purposes, and this just shows you the layout of the master file table in the placement within the master file table with this offset. So at offset 0, the master file table has its own record, followed by the mirror, the log file, as we saw previously. The log file is a record of all operations affecting a volume structure. And each of these is 4K in length, and the log file records file system changes as transactions. And we've actually tried to do a little bit of experimentation to determine exactly what each 4K log record means, and it's very difficult to follow, but essentially what it looks like it's doing is that before an operation occurs, let's say a read operation or a copy operation or a write operation, that information is copied to a log file entry, and then once that transaction is completed, then that's so indicated in the log file after that. Because essentially when we're doing some delete operations and write operations, we'll see multiple log records associated with that transaction. And so the log file is used for recovery purposes. So essentially what it does is it provides us some redundancy so that we're able to roll back the file system transactions to a steady state should, for example, your system go down, should it crash at an inopportune moment. And of course we know that Microsoft Windows never crashes, correct? It's a rhetorical question. Okay, the volume system file holds volume information. It holds the volume name, the version of NTFS, and this is what I was discussing before, is that you have multiple versions of NTS which are backwards compatible. Of course, can't be forward compatible. So it's starting with Windows XP. We had Windows 3.1. At Windows 2000, we had version 3.0 of NTFS. And with Windows NT 4, Service Pack 6A had version 1.2 of NTFS. And so the volume state, that should be, the volume holds the volume state, and essentially what that is if you recall from our discussions on the FAT file table, it holds a dirty flag. So when the system boots within the volume file, the volume state is indicated by a dirty flag, which means that files are being opened. And of course files have to be opened for the operating system to start working. And once you start shutting down the system cleanly, is that the operating system will look to see if every file has been closed properly, and if it does, it sets that dirty flag to clean, which means that everything is appropriate, all the files have been closed cleanly. If, however, there's some sort of crash on the system, then of course that dirty flag will remain set, which means that when the operating system is booted, if it sees that there's a dirty flag set, that means that there's an inconsistency within the files, and so then it can go out and make the appropriate corrections if need be. If you recall, there's a check disk function which is used to actually go in and correct the inconsistencies in the file system. And under Linux, if you recall, there's the FS check, which is used to do the same thing. And so all modern file systems that I know of use this dirty flag to determine the consistency of the state of the file system. Attribute definitions contain information about all file attributes that are defined on a volume. It identifies their properties, and a list of all attributes can be extended by modifying this file. Forensically speaking, this isn't very important. I haven't found anywhere where this information can be useful. However, that's not the same for the master file table, as well as the master file table mirror and the log file in particular. I've already seen that. The dot directory, the root directory, contains information about the volume's root directory, and it's an index of all the files and directories in the root directory. The bitmap files shows the allocation state of each cluster on the volume. And so 1 bit is used for each cluster, of course, either a 0 or a 1, indicating that whether a cluster is being used or not. And so a bit is set when the cluster is in use, and it's similar to a non-zero entry in the FAT table. So if we go over here and take a look at the bitmap file, as we see here, if you recall what this character is, if we look down here, the character indicates that in hex this is a 255, and so that means that 2 to the 8th power, right? So that would be 11111111, indicating that the first 8 clusters are in use. And so this indicates that all the clusters are in use, and then if we scroll down here, we're going to find somewhere in here, there we go, there's some. Notice that some of these, meaning that this cluster from, all the clusters from here to here that's represented by all these bits are not in use. Notice that only some of these are in use right here, and these are not in use. That looks like that would be 8 clusters here that are not in use. And this is just for your notes so you can see what is being used. This is the bitmap file here. Okay, the boot file, system file, is an entry for the boot record, and the starting location must be sector 0 for the boot. Of course, we already know that from the master boot record. And it can be up to 16 sectors in file if need be, and it contains the BIOS parameter block and the code define and load our NT startup files. And if we go back here, let's see if we can find this quickly. If we go back to the, whoops, I want to go back to the start of the, okay, that's just showing the log file. What I want to do is show the very first start of the directory, start of the hard drive. And here we are, this is it, offset 0. Notice it indicates it's NTFS. Of course, a lot of this is in hex. Notice that a disk error, read error occurred. NT loader is missing. NT loader is the bootstrap information required to launch the operating system. If we look here, here's the NT loader in the, where would this be located? If this is the first sector, that's going to be the second sector. There's also a backup of the first sector of boot that's located at the end of the volume, so that we have additional redundancy on the operating system. So if what we've seen thus far is a much more complex file system, I used the term operating system before, and I meant file system. We have a much more complex file system, and we also have one that's a lot more fault tolerant, because it provides much more redundancy than the FAT. The only redundancy we had in the FAT file system was the 2 FATs, and we had nothing else that was redundant. Okay, continuing on with boot, contains technical information about the partition, including the file record size, that is the size of each master file table record, which is 1024 bytes for these for NT 2000 and XP. I'm not sure about 2003. I don't believe it's changed. The number of sectors per cluster, the location of the master file table, and its mirror, and it's similar to the boot record under the FAT. Of course, it's going to contain a little different information than the boot record under FAT. And so typically it depends upon the hard drive size, but typically the number of sectors per cluster is going to be 8 sectors per cluster, because usually you'll find each cluster under NTFS is 4096. Bad clusters is a file consisting of all the bad clusters on the volume. And so the bad clusters are marked as being in use in the bitmap, and then it's similar to the bad cluster marker F7 under FAT. And I looked on this hard drive to see if I could find a bad cluster, and I could not, unfortunately. Well, fortunately, actually, that's quite good. So that means that we have a consistent file system. Okay, under Windows 2000 XP, we have a new file called Secure that contains all the security descriptors used on the volume, as well as their hash. And the reason we have a hash is to make sure that these don't change. It's another security, another piece of security information. And so a file's security ID is an index into the secure file. And what we'll see is that each file, each user has a security ID as well, and it's something called an SID. And the SID is used to distinguish between users. And we have uppercase, which is Unicode uppercase translation tables used to assist in sorting and searching of file names. And it is right here. Here's uppercase, and you see right here. Notice all this is in Unicode. This is the ASCII character set in Unicode. And we have extend, and I'm going to skip over this because I've never found a use for this information.